Assalamualaikum, hi everyone. So this is another video on chapter 1, reaction kinetics. So at the end of this lesson, what you should get is first, you should be able to define rate law, order of reaction and half-life, and then you should be able to write rate law with respect to the order of the reaction. Write the integrated rate equation for zero, first and second order reactions. And lastly, you should be able to perform calculation using integrated rate equations. So let's start with the first one, rate law, or also known as rate equation. Okay, so before we start with what is rate law or rate equation, like I mentioned in the previous video, you're going to learn a few terms. Okay, in the previous video, we already learned about the rate of disappearance of reactant. Okay, and then we also learned on the rate of formation. Okay, how to write down the differential rate equation. Okay, so for this video, we're going to start with rate law. So make sure focus on how to write down rate law. But before that, let's look what is rate law. Okay, so rate law is basically an equation that relates the rate of reaction to the concentration of reactants. Okay, it shows how the rate is affected by the concentration of reactant. Okay, so what does this mean? So let's take a look on one example. So we're going to start with a general equation. Okay, so given here a general equation, okay, AA plus BB to form CC and DD. So this is a general equation. So how are we going to write the rate law? Okay, so this is your rate law. Rate equals to K, concentration of A to the power of M, and concentration of B to the power of N. So please look closely here. Okay, so what you need to see here is on the rate law, we only write down the terms for the reactants only, A and B. And the power here, M and also N, is not the same as the stoichiometry coefficient here. It's a different thing. Okay, so in other words, to write down the rate law here or the rate equation, okay, it does not depend on the balanced chemical equation. Okay, so before that, so let's take a look on this equation. Okay, what terms do we have here? So where A is concentration of A, B concentration of B, K, here you are familiar with this. Okay, it's a constant, so in here we call it as rate constant. Okay, and M is order of reaction with respect. So here you should have with respect to A. Okay, and then N is order of reaction with respect to B. Okay, and M plus N will be the overall order. Okay, so M and N here are the order of reaction with respect to the reactants. And the order of reaction does not, like I said earlier, does not depend on the balanced chemical equation. So, if that being said, how do we determine the value of M and the value of N here? Okay, so by right, to determine this value, what we're going to do is, the value will be determined by experiment. Okay, only experimentally we can find the order of reaction for each reactant. Okay, now, so let's look on the next part. We're going to look now on the rate constant, okay, which is K. So what is rate constant K? So K is a proportionality constant for a given reaction. So this is the definition of K. So basically it's a constant. Okay, K is a constant at a particular temperature. So please bear in mind, like the constant that we used in previously in semester 1, the value of constant depends on a certain temperature. So as the temperature changes, okay, the value of K will also change. Okay, and that K does not change as reaction proceeds. Okay, unchanged with the change in concentration. So even though the concentration of reactant decreases, okay, the value of K is still constant. Okay, and lastly, the unit of K depends on the overall order of the reaction. Okay, so the overall order, like from the previous slide, okay, where we have rate equals to K, concentration of A to the power of M, and concentration of B to the power of N. Okay, so the value of K here will depends on, okay, the overall order of reaction, where to find the overall order of reaction, okay, we're going to add all the order of reaction that we have on our rate law. Okay, so which is M plus N. Okay, so the next one, we're going to look on how to derive the unit for our rate law. For our rate constant. So now, for example, what is the unit of K for a third order reaction? So let's highlight what we want to find. We want to find the unit of K, for a third order reaction. So we're going to start with writing down the rate law. Okay, so what is the rate law here? So since it's not given any of the reactants, okay, so we just assume we have one reactants and we're going to write it as A. Okay, so your rate law, you must start with rate. Okay, pardon me. Okay, so rate equals to K, concentration of A. Since it says here it's a third order reaction, so it's to the power of 3. Okay, so this is your rate law. So what are we going to find? We want to find what is the unit of K here. Okay, so to find the unit of K, we need to know what is the unit of rate here and also the concentration here. Okay, so as we learned before in the previous video, okay, rate, what is rate? Okay, so rate is change in concentration over time. Okay, so let's say our concentration, we put it as molar. Okay, our concentration, molar, and time is second. Okay, so the unit of rate will be molar per second. Okay, so let's write it down here. So molar per second equals to K. And then what is the unit for concentration? So since we already choose to use molar, okay, so for concentration of A, the unit will be M, capital M, molar. Okay, and then you have the order of reaction here, so to the power of 3. So to find the unit of K, rearrange the equation. So K equals to ms negative 1 over m cubed. Okay, so where okay, you will cancel this and you will get the unit of K for the third order reaction as m negative 2 as negative 1. Okay, so like I mentioned before, the unit of K will differ, depends on the overall order of reaction, okay, of each of your rate equation or your rate law. Okay, so now let's move on to the next part. So now let's look on the order of reaction. Okay, because I already mentioned about order of reaction, so let's take a look what is order of reaction. So order of reaction is the exponent of the reactant concentration in the rate law. It defines how the rate of reaction affected by the change of concentration of the reactant, and it cannot be predicted from stoichiometry because stoichiometry has no relationship with the order of reaction. So the order of reaction must be determined experimentally. So for this one, I already mentioned previously, okay, where on our general equation, okay, where we have rate equals to K to the power of A M to the power of B N. Okay, so the order of reaction, like I mentioned before, is this one. Okay, the exponent here. Okay, and the value does not affect it at all. We did not take the value from the balanced chemical equation. It needs to be determined experimentally. Okay, now, so we're going to look on the second point here. Okay, so what does it mean? The order of reaction define how the rate of reaction affected by the change of concentration of the reactant. Okay, so now let's take a look on the next slide. So let's take a look on an example. So I give you here a chemical equation 2NO plus 2H2 to produce N2 and 2H2O. Okay, so let's take a look on its rate law. So this is the rate law given. So as you can see here, the rate law given, K rate equals to K concentration of NO to the power of 2 times concentration of H2. And if you see here, the coefficient here, the power on your rate law, on the concentration of the reactants here, is not the same as the one that we have in our chemical equation. Okay, so like I mentioned before, this is because our balanced chemical equation, the stoichiometry here, does not influence our rate law. Okay, so you need to make sure when writing down rate law, the word rate here, you must write it down. This is the complete rate law. So if you just write your rate law, okay, without the word rate in front, so let's say you miss this one out, you just put equals to K concentration NO2 times H2. So this is wrong. Okay, it must include the word rate. And the value here, okay, which we call as the order of reaction, we will get it from experiment. Okay, experimentally or from experimental data. Okay, so let's take a look. So here, the reaction is we call as second order with respect to NO because we have concentration of NO to the power of 2, and first order with respect to H2 here. You have power of 1 here. So overall reaction order will be third order reaction. So make sure you understand this part clearly. Okay, and also understand that the rate law does not affected by the balanced chemical equation up here. So now let's take a look on the next slide. So just now I mentioned this. Okay, the order of reaction defines how the rate of reaction affected by the change of concentration of reactant. So what does this statement means? Okay, so let's take a look back on our rate law just now. So rate equals to K concentration of NO to the power of 2 times concentration of H2. So like we have mentioned before, for the rate of reaction here, the rate will be affected by the concentration of NO, okay, by second order reaction, and it will be affected by hydrogen by first order reaction, and overall the rate will be affected by a third order reaction. Okay, so what does this mean? So let's take a look on one example. The first one. Okay, what happened when I double? So doubling the concentration of NO and H2. Okay, what happened to the rate of reaction? So to tackle this question, okay, so let's take a look on a simple calculation. So the calculation will be based on our rate law here. Okay, So when I said I double the concentration of NO and also H2, what happened here is, okay, concentration, okay, sorry, let me change another color. Okay, concentration of NO from the initial rate law right now, we change it to 2NO. Why? Because we double the concentration. And also, concentration of H2 right now will be 2H2. Okay, so we're going to substitute this value here, this one, okay, sorry, we're going to substitute the value here into the rate law. Okay, so let's substitute. Okay, when substituting, you're going to write the rate law again. So it will be rate equals to K, but right now inside the concentration, instead of NO, it will be 2NO. Okay, 2NO to the power of 2. And H2 will be 2H2. Okay, so this will be the first step. Okay, the next one, after we did the substitution, we will rearrange the equation. Okay, so rearrange. For rearrange, we need to make sure that we will get the same rate law as the one we have here. Meaning in terms, our rate must be in terms of concentration of NO and concentration of H2 only. But right now we have inside our concentration 2NO and 2H2. So we don't want it to be like that. We want it to be like the original rate law. Okay, so what we will do here is we're going to rearrange by only leave NO and H2 terms. So it will be right now rate equals to K. So I have my K here. So what happened inside this term? Okay, so you will get actually, if we take out 2 to the power of 2 and then NO squared. Okay, and then for H2, we take out the number of 2 and then H2. So here only leaving NO2 and then H2, the same as our rate law. Okay, so the number in front of here, we're going to put it with the K. Okay, so we have 2 to the power of 2 equals to 4. Okay, times 2 here. So we will get 8. So it will be 8K, and that will leave us with NO to the power of 2 and H2. So if you can see here, right now, the new rate law that I have written here is the same as the original one, where we have K equals to, we have K concentration of NO to the power of 2 and H2. K concentration of NO to the power of 2 and H2. But the only difference here is we have 8 in front. So the number 8 here shows how the effect of doubling the concentration of NO and H2 done to the rate of reaction. So we can conclude here that by doubling concentration of NO and H2, okay, what happened to our rate? So we said that the rate will increase by 8 times. Okay, so this is a first example when we double the concentration of NO and H2. Okay, now, so let's take a look on another example. So what will happen when I halve the concentration of H2? So bear in mind here, our rate right now will only be affected by the concentration of H2. We only half the concentration of hydrogen. Okay, we did not change anything about the concentration of NO. Okay, so the same step that we did just now. So initially, our concentration of H2, okay, this is the initial concentration. So right now we change it as half H2. Okay, so the next step, we will substitute. So it will be rate equals to K, pardon me. Okay, so K, concentration of NO, since we did not change anything about it, so just write it down back. Okay, and then on the concentration of H2, it will be half H2. Okay, so substitution. So the next one is we rearrange the equation. So what we will do is we're going to take out the half here and we're going to put it in front. We will group it with the K. Okay, so now it will be half K concentration of NO to the power of 2 and concentration of H2. So please bear in mind, our target when rearrange the equation is to get the same term here. Okay, our term here must be the same as this one. Okay, that's our target. So from this equation, from this rate law, what you can see is the rate of reaction will halve when we halve the concentration of H2. So we can make a conclusion that the rate of reaction will be half. Okay, so why do I say the rate of reaction will be half? Okay, this is because from this part. Okay, when we look here, we have half K. Okay, so this is the part that will determine what happened to the rate of reaction. Okay, so now let's proceed to the next part of this video. So for the overall order of reaction, it can be any number based on what we have on our rate law. So for example, I have this rate law. So rate equals to K, concentration of A to the power of half and concentration B, so to the power of 1. What will be the overall order of reaction? So the overall order will be half from A plus 1 from B, the order of reaction. So total overall order of reaction will be 3/2. So it's not necessarily must be a whole number. It can be in decimal and it also can be in this term, okay, in fractions. So now for our syllabus, we're going to focus on 3 different order of reaction, which we have 0 order, first order and second order. So what does this order of reaction will tell us? So let's take a look. So this is our order of reaction, where we have here 0 order, first order and second order. Now let's take a look one by one on what does this order mean and what information can we get from each order of reaction. Okay, so the first one, we're going to look on 0 order. So for 0 order, it says that rate is not dependent on the concentration of the reactant. This is where we put the rate law as rate equals to K, times concentration of A to the power of 0. So as you know, any number to the power of 0, we will get 1. So we can also write the rate law as rate equals to K, meaning the rate of reaction only depends on the rate constant, or we can say that by changing the concentration of the reactants, it will not affect the rate of reaction at all. Okay, so as you can see here, it is said that zero order in A, so zero order overall. So like I said just now, if concentration of A is double, it does not affect the rate of reaction. The rate will remain constant. Why? Because when we look at this term, okay, our rate law here, rate equals to K. Concentration of A is not included here. Okay, so that's why changing the concentration of the reactants will not change anything. Okay, so next, let's take a look on what is first order reaction. So we can say that first order reaction rate is directly proportional to the concentration of the reactant. So we can write the rate law as rate equals to K times concentration of A. So as you know here, it's concentration of A to the power of 1. So it is said that the reaction is first order in A and first order overall. So what does this affect on our rate of reaction? So if concentration of A is double, the rate will double. So this is like the one that I taught you just now. Okay, when we double the concentration of A, we will put it as 2A. So rate equals to K, concentration 2A. So we rearrange the rate law. It will be rate equals to 2K times concentration of A. So here, okay, from this rate law, what you can see, when we double the concentration of A, the rate will double. This is shown by the value of 2K here. Okay, now, so let's take a look on what is second order reaction. So for second order reaction, it is said that rate is directly proportional to the square of the concentration of the reactant. So our rate law, we will write it down as rate equals to K times concentration of A to the power of 2. So we say that the reaction is second order in A and second order overall because we only have one our reactant here. Okay, only one reactant here. So what happened when I double the concentration of A? Okay, so if you look over here, when we double the concentration of A, okay, the rate will quadruples. Okay, what does it mean by the rate quadruples? How do we know it quadruples? So the same step that we will take, okay, we substitute A as 2A. So inside here, when we substitute A as 2A, okay, we will get rate equals to K concentration to A to the power of 2. So like we did earlier, so what will happen here is it will be 2 to the power of 2 and also concentration of A to the power of 2. So rearrange back the rate law. So you will get rate equals to 4K times concentration of A to the power of 2. So the quadruple part is here. Okay, if you don't want to say it as quadruple, you can also say that the reaction increased by 4 times. The rate of reaction increased by 4 times. It is also accepted. Right now, let's take a look on what is integrated rate law. So for integrated rate law, it shows the relationship between concentration of reactants and time. So for our integrated rate law, we're going to focus on the 3 order of reaction that we have mentioned just now, which our zero order, first order, and second order reaction. So let's start with zero order reaction. So for all these order of reactions, we're only going to consider a general equation, reactant A to form product. Now, how do we get our integrated rate equation? By combining 2 different equations. The first one here, we have our rate law, and here we combine it with our rate of disappearance of the reactant. So by combining this equation, we will get this equation, and we will do integration here. Okay, I will not show how to integrate this equation. What you need to know is you need to memorize this equation. So for integrated rate equation, for zero order reaction, it will be concentration of A naught minus AT equals to KT, where A naught here meaning it's the initial concentration of A, and AT here meaning concentration of A at certain time. So you need to make sure that you memorize this equation. It's either A naught minus AT equals to KT, or we can also use concentration AT equals to A naught minus KT. It's just a matter of rearranging the equation. So the time here is either you put second, minute, hour, depends on what type of data that we have. K is a constant value. So that's for zero order reaction. So now let's take a look for first order reaction. The same thing that we did for zero order reaction, we are combining two equations. The first one, the rate law for first order reaction, and we combine it with the rate of disappearance of the reactant. So by combining the both equation, the two equation, and we do some integration here, we will get our integrated rate law as this. So this is for our first order reaction, and the integrated rate law is ln A naught minus ln AT equals to KT, or when you rearrange the equation, ln AT equals to ln A naught minus KT. Just memorize the equation. And lastly, for second order reaction, we are combining the rate law for second order, rate equals to K, concentration of A to the power of 2, with the rate of disappearance for A, and for the combination equation, we will do some integration here, and we will get the integrated rate equation as 1 over AT equals to KT plus 1 over A naught. Okay, or you can rearrange the equation 1 over AT minus 1 over A naught equals to KT, and it's the same as zero order reaction, where A naught is our initial concentration of A, and AT is our concentration of A at certain time. Okay, so this one is general, so you need to make sure that if the question gives you a specific reactant, so let's say I have CO2 as my reactant, okay, and the reaction will produce some product. So it is said that the reaction is first order reaction. So first order. Okay, so what is the integrated rate equation for this reaction? So you will write down as ln, here change A into that specific reactant. So since my reactant here is CO2, so it will be ln CO2 naught minus ln CO2 at certain time equals to KT. Okay, so this will be your equation. So make sure you substitute the reactant correctly according to what's given. We will do some calculation involving the integrated rate law, but before that, we're going to look first on the half-life of each order of reaction, zero order, first order, and second order. So let's take a look. So what is half-life? Half-life is time required for the concentration of reactant to decrease to half of its initial concentration. It can be determined from the integrated rate law. So later, when we are doing the calculation involving the integrated rate law, there will be some question that will also involve the half-life. So we're going to look on the equation of half-life for each order of reactions. Let's look now on the equation for our half-life. Okay, we're going to look on each order of reaction, zero order, first order, and also second order reaction half-life. So let's start with the zero order half-life. So for zero order half-life, so the equation is actually being derived from our integrated rate equation. So if you look here, how do we get the equation for half-life for zero order reaction? Given to you, this is our integrated rate law. So from the integrated rate law, since from the definition of half-life, it's the time required for the concentration of reactant to decrease by half. So what you will see here is, okay, we will substitute this one, concentration of A, since it is for the half-life, so the concentration will become half. We just put the concentration at T as initial concentration over 2 and substitute back into the equation. So for the T over here, we can specifically put as T half, since we are talking about the half-life, and rearrange the equation until we get the half-life equation here. So from here that we said the half-life is directly proportional to the initial concentration of our reactant. How do we get this? It's from this equation. So it's directly proportional, meaning by changing the concentration of our reactant, the half-life will also changes. The half-life will also increase if we increase the initial concentration. If the initial concentration is lower, the half-life will also become shorter. Okay, so now let's look on the next one, which is for the first order reaction half-life. So same as the zero order, the equation we will derive it from the integrated rate law of first order reaction, where we have ln initial concentration of A, ln A naught over AT equals to KT. And please bear in mind, for this equation, the ln is for everything here. Okay, so the same thing apply. We take the T half here, we take the T over here as T half. So the concentration of A of our reactant at T will become initial concentration A naught over 2, because we are talking again about half-life when the initial concentration is half. So substitute inside the equation and we will get our half-life reaction for first order as this one, where T half equals to ln 2 over K. And if you observe here carefully, there is no initial concentration, there is no concentration of product inside the equation. So this means that the half-life does not affected by the initial concentration of our reactant. Okay, the next one, the last one, we're going to look on the second order half-life. So now let's look on the second order life. So as we did for the first order and the zero order reaction, the half-life for second order will also be taken from its integrated rate equation. We will derive the equation from here, where we will substitute the T over here as T half, so that the concentration at certain time will become the A naught, the initial concentration, over 2. So we will come to a conclusion that we will come to the equation of half-life T half equals to 1 over K times dA naught. So from this equation, we can see that the half-life is inversely proportional to the initial concentration of our reactant. Okay, now, so please make sure that you memorize the equation accordingly to the order of reaction. Make sure you do not mix it up. Okay? What's the importance of all this equation? Because later, we will use this equation to plot some graph. Okay, from that graph, we can determine another information and will be used to answer another questions. Now let's take a look on the calculation that involve integrated rate law. So example 1, at 1000 degrees Celsius, cyclobutane decomposes to 2 molecules of ethylene in a first order reaction with a very high rate constant of 87 per second. Okay, so let's highlight some of the information here and then classify. So the information given is a first order reaction for decomposition of cyclobutane. Okay, and given to you the rate constant. So rate constant is your K. Okay, so 87 per second here is actually the value of our K. This one. So the question, the first one, the initial cyclobutane concentration is 2 molar. What is the concentration after 0.01 second? So here, since it's a first order reaction, okay, we have a first order reaction, so all the equation will revolve on first order, meaning we have to use the integrated rate law for the first order reaction, and if there's any question about half-life, we will also use the first order equation. Okay, so question B, what's the fraction of cyclobutane concentration has decomposed in this time? So let's take a look on how to answer this question one by one. So this is our question with all the information that we have highlighted before. Okay, so for question A, the question asks here for the concentration after some times, the concentration after 0.01 per second. Okay, since this is a first order reaction, so we're going to use the integrated rate law. So the first thing that you need to do is write down the rate law. So since it's a first order reaction and our reactant is cyclobutane, you can write the rate law as this. So rate equals to K concentration of C4H8 to the power of 1. So you don't have to put number 1. So now, the next step, so since it is a first order reaction, the integrated rate equation that we're going to use is this one. Okay, ln C4H8 naught minus ln C4H8T equals to KT. So let's look back on the information that we have. So to find, we want to find the concentration after 0.01 second, meaning we want to find this part. Okay, what's the concentration at a certain time? So to answer this question, the information that you need to have is the initial concentration of cyclobutane, the value of the rate constant, and also the time. So if we look back, we already have the initial concentration here given to you. The initial concentration is 2 molar, and then K is given in the question and T is given here. We want to find the concentration after 0.01 second. So you need to be very careful about the rate constant and also the time. You need to make sure that the unit is the same. Okay, what do I mean by this? So if the rate constant is given in second, you need to make sure that your time is also in second, because there is sometimes in the question the rate is given in second but the time given is in minute. So what you can do is change the time from second to minute. From minute to second to match the rate constant. Okay, so now let's take a look on how to answer this question. So this is the equation again that we're going to use. So please make sure when you are writing down the equation, like I mentioned earlier, you need to change the reactants here. The one that we did for the general equation is A, ln A naught minus ln AT equals to KT. So please make sure when you are answering a certain question, when it's given to you the reactant, substitute the reactants here. So after you have your equation, substitute all the value that we have. So the initial concentration, so ln 2 minus the one that we want to find, ln C4H8 equals to our K 87, and then our time, make sure, like I said, the unit must be the same, is 0.01 second. Once you substitute all the value, so keep on calculating until you get the answer. So here, ln C4H8, you will get the answer as negative 0.1769, and the concentration of our cyclobutane after 0.01 second will be 0.83 molar. So please make sure your final answer is with correct unit. So this is how you answer part A. So now let's look at part B. Okay, now question B. What fraction of cyclobutane concentration has decomposed in this time? So we want to know how much of cyclobutane has decomposed. Okay, has lost, has gone. So the one that we have calculated for part A is the one left at 0.01 second. So for us to know how many has decomposed, how many is gone, what you can do is we're going to minus the initial concentration with the one left. So the fraction of cyclobutane decomposed can be written as this, the initial concentration minus the concentration at the time given, 0.01 second, over the initial concentration. So we just need to substitute all the information that we already have. Substitute all value. So we will get the answer, the fraction, as 0.59. So you need to make sure when we are talking about fraction, the maximum amount will be 1. It's 0 to 1. If you get a number more than 1 or smaller than 0, a negative value, so you need to recheck again your calculation. So this is example number 1. So now let's look on example number 2. Now, example 2. Cyclopropane is the smallest cyclic hydrocarbon. It is thermally unstable and will rearrange to propene at 1000 degrees Celsius. So the rate constant for the reaction is 9.2 per second. So we have two questions here. What is the half-life of the reaction and how long does it take for the concentration of cyclopropane to reach 1/4 of its initial value? So for this question, let's take a look on what information do we have here. So the question gives you our reactant is cyclopropane and given to you the rate constant for the reaction is 9.2 per second. So the first question is asking for the half-life of the reaction. For us to know the half-life, to calculate the half-life, we need to know which equation will we use. We have zero orders, first order and second order. So for example number 2, it is not stated what is the order of reaction. Okay. Even though we don't have the information on that, it's not like we don't have the information. It is just not stated in the question, but the information is actually in the question to determine the order of reaction. So 9.2 per second, so this is our K. So the clue here is from the unit of the rate constant. So previously in the earlier part of this video, I already told you the unit for rate constant will differ depends on the overall order of the reaction. So same goes for 0, first and second order. Each of this order of reaction will have its own unit of rate constant. So if per second as -1, which order of reaction does it belong to? So before we proceed with answering the question, I want to show you the unit for all the order of reaction, 0, first and second. So here you can see the order of reactions with its rate law. So now let's derive the equation for each of the order of reaction. So let's start with zero order. Okay, the unit of rate will always be molar per second. It's not going to be per second all the time. Depends on the unit of time given. But generally we're going to use second. So here, since rate equals to K, so directly we can see here that the unit of K is molar per second. So now, let's continue with first order reaction. So rate, molar per second, K. So we have concentration of A. So the unit for concentration is molar. So let's rearrange this equation. So molar per second per molar. So from here, you can see that the unit for rate constant for the first order reaction will be per second. Okay, now let's do for second order reaction. So rate still the same, molar per second, K. So now concentration is still molar. It's just that for second order reaction, we have to the power of 2 here. So rearrange the units. So ms -1 m2. Okay, so you can cancel this and we will find that the rate constant unit for second order reaction is per molar per second. So by determining and looking at the unit for the rate constant, we can know which order of reaction do we have for our question, for our reaction. So now let's go back to our question and determine which order of reaction it is. So as you can see here, we have S -1, meaning what order of reaction do we have? So if we look back on the slide before, on the one that we have discussed just now, S -1 is for first order reaction. So once we have determined the order of reaction, then we can choose the correct equation to find the half-life of the reaction. So now let's proceed with the calculation part. So this is our question with the highlighted information. So the first one is, what is the half-life of the reaction? So since we have determined that the reaction is first order with respect to cyclopropane, so the half-life equation that we will use is half-life T half equals to ln 2 over K. So we substitute all the information that we need. We only need the value of rate constant. So substitute the value ln 2 over 9.2 and you will get the answer as 0.075 second. So please make sure that you write the correct unit. Again, if your answer, the value of your answer is correct but you put incorrect unit or you did not put any unit at all, so there will be no mark for the final answer. So now let's proceed with part B. So question B, how long does it take for the concentration of cyclopropane to reach 1/4 of the initial value? So we want the value 1/4, 1/4 of the initial concentration. So how are we going to do this? So let's start with the initial concentration first of cyclopropane. So it's C3H6. So this is the initial concentration. Once it undergoes the first half-life, okay, so let me label here half-life 1. What happens to the initial concentration? It will become half. So we write down as half C3H6. We are still, we only have half of the concentration right now. What we want is quarter. How do we get quarter? By dividing this equation here, this concentration, by another half. 1/2 divided by 2, we get 1/4, meaning it will undergo another half-life. So we will get the second half-life here for us to get 1/4 of the initial concentration. Okay, so let me put not here. So now, this is the information that we have taken out. Okay, for us, sorry, this is not 1/2. For us to get 1/4, 1/4 of the concentration of cyclopropane. So since the reaction is a first order reaction, so the value of the first half-life will be the same as the value of the second half-life. So each order of reaction will give number of half-life, different half-life. So from the one that we have discussed before, for first order reaction, the value of half-life is directly proportional to the initial concentration. So that's why here the value of half-life will be the same. Okay, for this one, it will you will get a clearer view later when we look on the graph of concentration against time. Okay, so that we can see the half-life. So for now, this is the information that we will use. So the time taken to reach 1/4 of the initial concentration of cyclopropane will be 2 half-lives. So 2 half-life, and the value of half-life, we already get the value from part A. So just substitute the value. So 2 times 0.075. So we get the answer as 0.15. Sorry. Okay, 0.15 second. So we have finished our examples. So that will be all for today's lesson. So with your note, I already included a table for a zero order, first order and second order reaction where you have all the rate law, the units and all the graph included for each of the order of reaction. So please take a look and make sure you understand all the graph, the equations and everything. So next, what you can do is try the exercises and then mark your answer. So if you have any questions, any problems, do ask me. So with that, thank you.